the polycopy of quantum optics 1 lasers. In this course, we will study namely how lasers work, how to manipulate them, and how you can use them to make ultra-short pulses. We will start with studying the light-matter interaction to see how light interacts with matter, because that's at the core of the laser. And then, And then we are going to analyze the how light interacts with matter using two models. The first model will be the model of the time-dependent perturbation theory model, and the other model will be something called a Rabi oscillation model, a two-level system. And after we've seen how light interacts with matter, as in how light excites matter, we will then go to the second half of the feedback loop and see how the excited matter affects light itself. So how does light propagate through that excited medium or the active medium? Now, of course, once we have studied that, we shall then go on to studying the actual working of the laser. Therefore, we're going to have to study the gain capacity, and we're going to study the gain and its saturation as the intensity of light increases. We will then, of course, go to chapter 3, where we'll study the oscillation. So now we've covered all the microscopic or wave components of the laser, and we shall go to just studying the microscopic classical electromagnetic laser oscillations. What are the conditions for proper oscillations? We're going to study something called a continuous wave operation regime, and we're also going to study something called a transient regime in chapter 5. But of course, the continuous regime will be explored much more than anything else. We will look at how we can have 2, 3, or 4 level lasers, and of course, we'll see how 2 level lasers aren't actually possible realistically, so we only have 3 and 4 level lasers to study. We will look at the gain curve, study broadening, both homogeneous, inhomogeneous, why it happens, what its consequences are. And after that, we will move on to the modes of the cavity. So we will look at the longitudinal modes, as in plane wave propagation modes, but we will also look at something called the Gaussian laser mode, where the laser light propagating inside, instead of having a plane wave profile, now has a Gaussian profile, or even more complex, a Gaussian Hermite profile. But we shall not study the mathematics of that too much. Then, of course, we shall keep studying laser and the continuous wave regime, but now we will give lifetimes and decay rates to our population inversions and our cavity itself. And we will study 2 kinds of lasers, which is a class A laser and class B laser, and we're going to explore the steady state solutions for them and see that there's going to be 2 solutions for each kind of laser, and we're going to see how those 2 solutions, how their stability is and how perfect they are in oscillations. Of course, we're then going to see multimode operation, which we'll have previously ignored, and see how in the presence of various modes in the laser we can have competition between the modes, and depending on the criteria, which mode wins. Then, of course, in chapter 5, we will move away from the steady state regime and study the transient regime, so the regime where the laser is just turned on, and the regime where the laser is about to reach steady state. Of course, we'll study the stability of the laser around the 2 solutions we had before for the steady state. And of course, using this, we'll find out that actually we can create in our class B lasers something called big pulses in multiple variety of methods, 2 of which are called the Q switching method and the laser mode lock-in method using frequency comms. We will also see something called spiking, which can also be used to create laser pulses, but they are not so as powerful and efficient. And then, of course, we'll finish chapter 5 by studying something called chirp pulse amplification, where you use a method called chirping, which is due to the propagation of laser light in the medium and the broadening to, of course, create very, very small but powerful pulses. A very, very, in the time domain, very tiny time domain. And of course, something I didn't forget to mention is we're going to see how frequency combs in the mode lock-in regime can be used to measure time itself or the accuracy of the pulses themselves. Now, finally, we will then go on. Until now, we'll have studied everything in the deterministic regime, meaning the amplitude of the laser is known and the phase of the laser is known deterministically. Then we see why that description of laser light is not complete, because we're ignoring fluctuations of course, physical parameters. We're also ignoring fluctuations of due to spontaneous emission in the laser, and so we're going to have to employ a noise-based description of laser light, aka a statistical description of laser light, and we're going to have to develop our rate equations in the form of Langevin equations. We're going to then study Langevin equations a bit, just normal properties of Brownian motion, ergodicity, and of course something called the power spectral density related to the Wiener-Khinchin theorem. But of course then this will be applied to the lasers in terms of the Langevin equations, and we're going to use this random process to define a line width of the laser, which is the minimum width a laser light can have in the frequency domain. Due to these random processes which just cannot be eliminated. And we're going to finally see how to detect these spontaneous emission or more statistical fluctuations in our laser light using two-wave interferences and seeing the beat note between the two lasers. This chapter particularly focuses a lot on the correlations and how you can use the correlation to convert to the frequency domain. And that will finish the working of our lasers. But in today's lecture, we're going to study the first chapter, which is the interaction between light and matter. And so, let us begin. But let's see if I can pause.